Okay. So I have some announcement. So this Friday we will have a quiz. This quiz number 6. But that quiz is actually remote. So that means you don't have to come here, and you don't have to show up here. So actually, I'm attending a conference next week, robotics conference in Macau, and so I have to be there, and so I cannot uh, make this Friday. So this Friday we will have a quiz, but the quiz will be through eCampus. Okay, so you will just log into the eCampus, and the quiz will be there. Just download it, solve it, take a picture of it, and just upload it. Um, but you'll be given some time, so you cannot. It's not an unlimited time, so it's like you're given like 20 minutes or 25 minutes. So you can just, if you just start it, then you have to upload the file within that time. Okay. So you can. That's what we're gonna do, and then. So for this Friday, yeah, that's it. It's like an exam, okay, but it's just a quiz. And then another one is so for the next week. So since I'll be gone, so there's no physical attendance required. I mean, not required, but you don't have. You can come here, but no one will be here. So, but again, I'm gonna post the video lecture. Okay, so it will be about using Python to do the simulation of dynamics that you have derived, right? So we studied how to derive equations of motion. Then how do we use it in our simulation in Python? Right? Well, even though you can do it in MATLAB, but I personally are more expert in MATLAB coding, but um, actually I'm transitioning to different languages now. Python isn't one because many people are using Python, but actually I personally use other language called Julia, which is a computational programming language. So I use it for graduate school for research, and it's a lot more powerful than MATLAB or Python. But since you have some experience in Python, so I'm using it. There are some limitations in computational, numerical computational things in Python, uh, but that's what we can do at this moment. Okay, so um, I'll cover that. I'll cover that one. So with one example that we handled during the lecture, uh, I'll show you how to do the simulation in Python, and also I'm going to share the code so you guys can study that and download it, run it, and then also I posted a question, the description about the project. Okay, so you go through it. I try to give the details about it. So um, if you just read it, then everything is very straightforward. But let me just briefly mention about it. So it's about the deriving equations of motion and do some analysis of those systems. Um, and very simple control. I don't expect that much very good control, but just want to see you just try it. Okay, so but anyway, the most important thing is you choose two problems. I mean two examples, okay, and then you just set up everything correctly and derive the equations of motion as we did in class. Okay, but also, then what's the appropriate topic? Can I just do simple mass spring damper system in two-dimensional? And the answer is no, you cannot. Okay, it has to have fairly complicated dynamics. That means it has to be in three-dimensional. It has to be uh, it has to involve at least two or more generalized coordinates. Okay, so that means it's multi multi-body dynamics. Okay. So maybe this one, the one that's shown in the lecture note on screen, that's about what I require, or a little bit more complicated, but maybe gyroscope is a good example. So 3 or 4 generalized coordinates are about what I want. Okay. So and I gave some examples on eCampus. So you just click the PDF file, then you'll see some example figures, but they are just examples. Okay, you can choose your own thing. If you think, for example, if you go to amusement park and there's roller coasters and very complicated structures and geometry, then if you're interested, then you can try that as well. But if the number of generalized coordinates becomes more than 5, then it's going to be very complicated. Maybe I can show you one example. Let me see if I have it. So, for example, this is an example for 5-link humanoid robot walking dynamics, and so everything else is the same. It's just the same process, but then now if you just run the EL equation, it looks like this. That means it's too complicated. I mean, it's too long, so Mathematica refused to show all the equations. But if you just do some simplification about mass matrix is basically never mind. I don't have to. It's just like a inertia matrix, but that inertia matrix looks like this, as you can see. But it's simplified version. But if you run, well, actually I didn't run it, so I cannot show you the actual one. Let me see if I can show more. Okay. Yeah, I have to run it, but it's quite complicated. And here you see aborted. The reason why I aborted is I try to simplify the Q1 double dot, and then as you can see here, it spent more than 300 seconds, and so it couldn't finish that simplification within that time. So if I want to proceed, then I have to increase that time limit. So again, if the degrees of freedom becomes 5, look like 5 is not that complicated, but computationally, the equation of motion is very complicated. Okay. So as I said, maybe 3 is enough. So in our example here, even though this is a 3 degrees of freedom problem, but we didn't actually see that complicated equations. That's because we assumed that the bar is massless, and also this one is massless. But if you have mass in both, now it's crazy. Okay. So that's why, even though we had this example, it was doable. But maybe you can try with paper and pencil. But now, if the mass and inertia are added for reference frame A and B, then now it's very complicated again. Okay. So that's why I still recommend the degrees of freedom to be 3. Or if you want to try 4, is maybe doable, but you have to use the toolbox. Okay. Any questions? Yeah.
The portion on the quiz on Friday, is it only going to be available during our class time, or are you going to make it?
No, you can do it during Friday anytime. But anyway, you will be given like maybe 20-something time slot. Did you have a question before?
Oh, I was just asking. So there's no class Friday and then all of next week?
Yes, I'll gonna make an announcement and send you guys an email about that. Okay. Any other questions? If not, then now, so I was mentioning about lectures next week. So the first one was Python simulation method. The second one is I will do more examples of using Lagrangian method, especially that's something more complicated. I mean, the system with the complication like gyroscope or the rolling coins. Okay, so I'll do one example, especially how to set up the coordinate systems, reference frames, or generate coordinates. So once I'm done with that, then I'll move on to the next topic, which will be controls. So today I'm gonna do another simple example, actually simpler example than this one, okay? But then it's a little bit different because now the system it seems like it's floating, but let's see what we can do. Because even though we studied how the Lagrangian mechanics and equations, but still you're not that familiar with how to apply it in more general cases. So we'll do some examples here. So the one that I covered in here is just one example. Right? So let's see what we have in here. So the example that I'm going to do is this. Say we have a surface, it's frictionless. Frictionless surface, and we have a wedge. Let's say that angle of the wedge is theta. But that theta is not a variable, it's just a parameter. So that means I just use theta as a parameter, but that value is fixed. Okay. So don't be confused that this theta is not a generalized coordinate. Okay. Now I have a block mass M. Let's say this is the wedge is mass 1, M1, and this one has M2. Okay. And also at the contact it's frictionless. Alright, so obviously we have the gravity in that direction. Then what do you expect? Let's assume that there is no initial condition. You just hold it and just release it. And what happens? So the wedge, this wedge will slide in this direction because of the mass, the weight of the block. And due to the gravity, the block will also slide down on the wedge, right? So that's what's gonna happen. So if you just see the whole picture, then this one will move in this direction, and this will move on in that direction. Okay. So that's our system, and very simple. But now there is some interaction because this one, if this wedge is fixed, then obviously the movement of the block is just a straight line. But since this wedge is moving to the right, and now if you just look at the movement of the block itself, it's not a simple straight line, but it will be something like this because of that relative base movement, right? So so then let's solve this problem. So what do we have to do? So let's assume that this is your project. So what do we have to do? Yeah, so coordinate system, or more general, to be more accurate, we have to define reference frames, right? So first define reference frames. And so our reference frame in this case, first you have to start with the Newtonian reference frame. So in that case, I can say, so we have N1, N2. Obviously, N3 is out of plane. So that's our Newtonian reference frame. And how many reference frames do we have other than the Newtonian reference frame? We have two, right? One is a wedge and the other one is the flap on the wedge. So I can say this is reference frame A and this is reference frame B. Then we want to add A1, 2, 3 and B1, 2, 3 appropriately. So what is A1, 2, 3? How is it defined?
You probably want to make it the same as the Newtonian.
The same as N1, 2, 3. Do you agree with that? I mean, the same orientation, right? But not the same location. But but make sure that A1, 2, 3 is fixed to rigid body reference frame A, right? So let's do this one. Then we can try this. So we have A1, A2, and obviously A3. But make sure that that is fixed to rigid body reference frame A. Now, what about B1 to 3? So one possibility that the B1 to 3 has to be attached to the rigid body reference plane B, right? Then one possibility is you just use the same orientation like this, or maybe you want to align it such that one direction of the triads are aligned with the slope. Right? So that means one possibility is you just do this. So which do you think is better or easier? The second one, aligned one, yeah, slope one, yeah. So I like that too, because so when you assign the reference plane, you have to think about what is the possible movement of that single degree of freedom or that single generalized coordinates. Okay, that is the question. So obviously, it's a good way to define your reference frame like in this way. So we have B1 hat and B2 hat. Okay. So we're done. Okay. So we define reference frames, and second is what is it? So define. What's the next step? Before that, defining rotation matrix. What do we have to do? Generalized coordinates. Okay. Define generalized coordinates. Okay. So I use Q1 and Q2 here because we have only 2 degrees of freedom. So 2 DOF. So Q1 and Q2. So how do we assign Q1 in this case? So what is Q1? The sliding movement, or sliding movement of reference frame A. So then we can assign. So this one as Q1. Then what about Q2? What about Q2? Angle between this one and this one? I mean, this? So what is Q2 describing? Motion of B, and you just assume that your reference frame A is fixed. Okay, then your Q2 is describing the relative movement of this reference plane B. So then what we can do is, let me change the color here because I have too many blues here. So let's assume that there is some possible origin, okay, where the Q2 is considered to be 0. Then you can determine the distance or the position of reference frame B to be Q2. Does that make sense? Okay. So again, there is no ways of assigning your reference frames mechanically. That means without thinking, you cannot simply just assign Q1 and Q2. There's no canonical way. You just have to think about what is the possible movement of the system. Okay.
With Q2 going the opposite direction of V1?
That's fine. It's negative then, right?
Okay, so it's
Yeah.
negative.
So that's our Q2, right? Okay, then so we just define generalized coordinates, and so now the third one is you have to define direction cosine matrix. Okay. So what is the direction cosine matrix or rotation matrix for reference frame A? Reference frame A or DCM for reference frame A with respect to reference frame N. Or sometimes I call it rotation matrix and NAA. So how is it defined in this case? Is there any rotation involved? There's no rotation, so that means orientations are the same, right? So it's just the identity matrix. So this is a little bit different thing that we saw from the one that we saw in the previous example, right? Because the previous example, we everything was about the angle, rotation, right? But now here, there's no rotation at all. But still, we have to assign the generalized coordinates Q1 and Q2. In this case, Q1 and Q2 are related to the translation only. No rotations involved. Right? What about the same thing? So now in this case, rotation matrix of reference frame B with respect to A. So what is it in this case? It's rotation by theta about what axis? Z-axis, right? So N3 or A3, it doesn't matter. Or even B3, they're the same. So it's rotation by theta about the z-axis. In other words, it's simply cosine theta minus sine theta, cosine theta, 0, 0, 0, 0, and 1. Okay. So we define our direction cosine matrices. Now, if we're using Lagrangian method, Lagrangian mechanics, to do it, we have to first define kinetic energy and potential energy. So to find the kinetic energy and potential energy, what we have to do first is we have to find, for kinetic energy, we have to find the velocity, right? And also angular velocity if it has rotation. Anyway, to find the velocity, what do we have to do? We have to so find position vector velocity vectors, okay, especially of the center of mass, okay. Center of mass of reference frame A and B. So what is it then? So we actually have two center of masses in this case, right? So the first one, maybe the position vector, I'm going to call it POS A. Well, it's just a naming. You have to use your own naming, right? So what is it? The center of mass of rigid body reference frame A. So it's Q1 in A1 direction or N1 direction. Well, it may have some vertical movement, but it's just fixed one, so you don't have to consider that fixed value. So what you can do is just Q1 A1 hat. Now what about the position vector for center of mass for rigid body B, reference frame B? Well, here, let me just mention that. Ignore fixed values. Okay. So now, here, so you have Q2, right, in this direction. But it's obviously, if this one is moving in this direction, this is minus, right? So we have minus Q2 in B1 direction, but that's relative movement, right? Because if you just assume that this is the origin of the system, then this origin is also moving to the right by how much? The same movement that you saw from the rigid body A. So you just basically add the position vector for the reference frame A first. So it has to be there, and then now you take the difference, the subtract this Q2 in B1 direction. Okay. So that's our position vector. Yeah.
How do we consider vertical, the vertical?
Yeah, vertical position, again, it is needed if the rotation is involved, because then now the moment of inertia, it's all about the how far you are from the center of mass. In that case, you have to consider you have to consider the actual position. Okay, so the height is important. In that case, you have to add that. But now, as you can see, there's no rotation involved at all. So that's why we're not considering that one. And the reason why also we are doing this one is, if you're just computing the velocity, what matters is the velocity, right? Because we have to calculate the kinetic energy, and kinetic energy is only about the velocity. So if you have some fixed constant part here and constant part in here, you have to differentiate it anyway. Okay. So that won't show up at all. So you just get the velocity of A, velocity of B. Then your kinetic energy is just half mv squared. In this case, our v is your velocity. Let's say this is VA and this is VB. Then we have VA dot VA plus F, oh, okay, this one is M1, M2 VB dot VB. So that is all we need, right?
I'm still confused on like, so why don't you have to consider the fact that it has velocity going downwards?
No, that's already included. I mean, so your position vector B, this one doesn't involve any vertical movement, but your B1 vector involves vertical movements. And our position vector, potential energy is mg. So in this case, since the wedge doesn't contribute any potential energy, only m2, right? So it's just m2gh. Now you have to compute the h part, right? So that one is what you need to do. So that means this is coming from your position vector B, okay? Only n2 components. So you have to do that. And finally, your Lagrangian is k minus u. And once you have that, your dynamics equation is simply round L round Q1 dot minus round L round Q1 equals some torque or force. In this case, it will be force. It's straight movement, translational movement. But what are the forces that we need to add in this case? Do we have any external forces other than the gravity? We don't have any other forces. This is just a free movement, right? So we can just simply set this one to be 0. Okay. And the same thing for the second generalized coordinates, Q2. And this is also 0. So that's all we need to do, right? So let's do a coding, okay? So let's do it together. And so as you can see, the current version is 0.83. So download that. Initialize it, and we have reference frame A and B, so remove that. So we have reference frame A and B. Generalized coordinates Q1 and Q2. Direction cosine matrices. The first one is just the identity matrix. So you can just simply type identity matrix. Identity matrix, and you have to define the order, which is 3 by 3, right? Or if you don't know that function, then you simply just put 0 in here. That's fine. Okay, it will also give you the identity matrix. Okay, so that's what we have. And the second one is relative, but it's still, you don't even need to have the relative command in here because they are anyway the same. Now it's about the rotation about z-axis. The angle is theta, so let me just put theta in here. Okay. Any questions? That's very straightforward, right? And so run it. we don't involve any rotation, so just forget about omegas, right? So I'll just comment that out because we are not using them. Okay, now let's define our center of mass position. The first one is position of reference frame A, the center of mass, which is what, Q1 in A1 direction. Yeah, in A1 direction. Okay. And then the second one is the position vector B, COM. It's just this one plus now Q2 in B1, but it's negative, right? If you remember this, it's negative there. Okay. Now, once we have that, then what do we have to do? So let's run it first and see what happens. So that's our position vector. Then now you can just compute the velocity by just simply differentiating it. One way of doing that is what you just use the vector differentiation formula. So that means you just convert this one. Well, you don't have to convert it, but you can use a vector differentiation formula like this one. But then here, to use this one, you have to define angular velocity. Well, but in this case, since we don't have an angular velocity defined, we can just simply so if you read this one, so you have to first yeah, so let's simply add that. So we have position vector A, and your first reference frame, both are n and n, right? So because we have differentiated in Newtonian reference frame, and we just expressed it in terms of reference frame n. Just simply run it, and you'll get this. This is very obvious, right? Just Q1 dot. Do the same thing for the second one, 3. And now it's a little bit more complicated because now you have B1 involved in the vector. So we just found the position of velocity. So let me just assign a variable here, VA. This is VA, and this is VB. So let's define our kinetic energy. It's half M1. Now you have to do the dot product. So VA and VA, right? And just copy that, paste. Now M2, VB and VB. Okay, that's our kinetic energy. And we have to compute the potential energy. So what is potential energy? U. It's M2, G, and H. The H is what? Is a position vector. So you just get the position vector, but express it in terms of reference frame n. Okay, so we'll just use our unify, and so we're gonna get the coordinates. So then it's position vector B, and we want to express it in terms of reference frame n, and so get the second component, which is the vertical position. So run it, then you'll get this. So we got kinetic energy and potential energy, and so just define Lagrangian, which is k minus u. So we now have the expression for this. Okay, then what? We have to now use Lagrangian mechanics equation. Well, in my toolbox, in her toolbox, I have other functions that can evaluate the Lagrangian equation automatically for you guys. Let me just not do this one at this moment, because you have to be familiar with that equation first. So let's simply use our original equation, which is this, right? Which is this. So let me just do it manually using d function in Mathematica. So first, you just define round L, round Q1 dot. Okay, so let's do that. So round L, so L, we just differentiate L with respect to Q1 dot. So it's Q1 dot. So that's it. And then now differentiate this one with respect to time. So this whole thing with respect to time. And the second term, which is this one, minus round L, round Q1. So minus, so now L, Q1. So that's the equation. If you evaluate it, then this is the equations that you get. Very simple, right? Now do the same thing for the second generalized coordinate. So we have Q2, Q3. So now you have two equations. Okay. This is very simple but powerful, right? So by just studying, where is it? So by just studying these two equations, you now can describe the movement of theta, the wedge and the block. Okay, but then one thing that you have to make sure is that if you look at the first equation, so you have Q1 double dot and also Q2 double dot here, Q2 double dot here at the same time. So that means it's actually coupled. So the two systems are coupled. They're affecting each other. And the same thing happens in here. Okay. The second equation is about the block, right? Even though the block it seems like it's on its own, but it's affected by your Q1 double dot. The Q1 movement, if Q1 movement is there, then also the movement of the block is affected. Okay. So that's what we have. And then the next question is, so actually we're done, okay? But then the next question is this. Here. So if you look at the contact point here, there should be some forces in between, right? The reaction forces. So what are those? What are the reaction forces? That is our question. Okay. So if the block, no, the wedge is fixed, and what do you think is the reaction forcing? What is it? It's just the weight of this block but then you have to decompose it into the normal direction, right? But now the wedge is also moving. Do you still think that the reaction force is just the weight of the block, or smaller than that, or bigger than that? But the answer is actually it's not just the weight of the block. It also involves the weight of the wedge as well. Sounds very interesting. So we'll cover that problem. And to do that, now, what is the appropriate way of doing that? So we have to consider the reaction force in between these two. So what do we have to do in this case?
Find the normal force to find the friction.
We don't have any friction here. Right?
The last thing we had in third grade. The x and the rotation.
Your approach is good, but it's not about adding new reference frames. It's just adding new or extra generalized coordinates. That is actually, now here we're assuming that this block is always making a contact with the surface at the surface, right? But that doesn't have to be, right? It doesn't have to be. It can move freely, and so that means this block can move freely up in the air. If you can do that, right, that means we have to assign another generalized coordinate in that direction. Then now our question is, we can set this third generalized coordinate to be 0. So that's our constraint in that case. And you have to find the constraining force. Okay. If you can do it, then that constraining force is the normal force that's making this block to be always in contact with the wedge. Okay. So that's what I'm gonna do on Wednesday.